Hello, everyone. So today I'm going to talk about the biomimetic mechanisms, and this work previously appeared in EC19, and this is joint work with my advisor Shuchi Chawla and Crystal Samos. So we are consider the Bayesian multi-item revenue maximization problem, where a seller would like to sell n items to a single buyer, and we assume that the buyer has private value function defined for every possible set of items, but his valuation function is unknown to the seller. In the Bayesian setting, we assume that the seller knows the distribution of the valuation function, for example, by learning from some historical market data, and the objective of the seller is to maximize the total revenue obtained. So let's start with an example in this setting. Suppose that the seller would like to sell a sandwich and a drink to a buyer, and the buyer's value for a sandwich is uniformly drawn from 1 and 3, and buyer's value for a drink is uniformly drawn from 1 and 2. So it is known that any single buyer mechanism can always be represented as a menu of choices. For example, the optimal mechanism for this setting is as follows. The buyer can either pay $4 and get both sandwich and a drink, or pay $2.5 and get a drink for sure, and then toss a coin. And if the coin goes to a head, he also gets a sandwich. So it's known that the optimal mechanism for multi-item setting can be very complicated and has many unnatural properties that make it hard to analyze or compute. So recently, there are a lot of working on using a simple mechanism to get approximately optimal revenue. So let's start with some notation. Suppose that op denote the optimal revenue obtained by any randomized mechanism. Drev denote the optimal revenue obtained by optimal deterministic mechanisms. Srev denote the optimal revenue obtained by item pricing. And the Brev denote the optimal revenue obtained by pricing the entire bundle. So there are previously numerous results working on using simple mechanisms to get approximately optimal revenue in the settings where the buyer's valuation functions are restricted, for example, the sub-additivity, and the value for each item are independent. So on the other hand, if we do not have the independence over the value of the items, it has been shown that the revenue gap between optimal revenue and the optimal deterministic revenue can be infinite, even for additive or unit demand buyers. And the revenue gap between optimal revenue obtained by deterministic mechanism and item pricing can be exponential in n, even for additive buyers. So is it really impossible to get a positive result for general value buyers? So in this talk, I would like to propose an alternate approach that you would like to propose a different benchmark rather than the arbitrary optimal mechanism. And we want to place some reasonable restrictions to the class of mechanism that we want to optimize. So what do we mean by reasonable? So let's see this motivating example. Suppose, again, we want to sell a sandwich and a drink to an additive buyer. With probability 4 over 7, the buyer has value 0 for a sandwich and 1 for a drink. With probability 2 over 7, the buyer has value 2 for a sandwich and 0 for a drink. And with probability 1 over 7, the buyer has value 4 for both items. So we can compute the optimal deterministic mechanism for this setting. So we may observe that this menu is a bit weird. So if I go to this restaurant and I see this menu, and if I want to purchase a sandwich and a drink, I would just try to purchase the second menu entry and get a sandwich, pay $2, and then pay $1 to get a drink. So in this way, we are getting a cheaper way to purchase both sandwich and a drink, so the first menu entry seems a bit redundant. So the same thing happens to the optimal randomized mechanism. So we can still observe that if I want to purchase a sandwich and a drink, I can first pay $2 to purchase a second menu entry and get a sandwich for sure, then try to repeatedly purchase a third menu entry. So each time I pay 2 or 3 and get the drink with probability 2 or 3, then in expectation to get a drink, I only need to pay $1. So in this way, we still get the sandwich and drink for $3, and it's cheaper than first menu entry. So the question we want to ask here is that how would the previous results for multi-item mechanisms change when the buyer is allowed to purchase multiple menu options? So let's go to the definition of the class of mechanism we studied, that is the simple proof or by many mechanisms. So in security, simple attacks means that the attacker creates multiple false identities to gain huge influence. And similarly, we define in mechanism design the simple proof or by many mechanisms to be the class of mechanisms such that the buyer is allowed to purchase any multi-site of menu options at the sum of their prices. And then the buyer can obtain an independent draw from each option and get their union. So a specific case of this class of mechanism for deterministic mechanism, by many mechanism is simply equivalent to the class of mechanism we have studied a lot, that is monotone subadditive pricing. So there have been previous results saying that the optimal mechanisms may not be simple proof even for additive buyers with independent valuation function. And we want to ask, is optimal revenue of by many mechanisms still infinitely better than simple mechanisms? So the answer is false, and now we propose our main result.
Could you say again what happens when you have randomized entries? How do you, if I go twice and buy 2/3 of a Coke of can?
Yeah. So I can first go to the shop and try to purchase this menu entry. If I get it, I will stop. And if I do not get it, I will go to the shop again and try to get the menu. So this is the adaptive setting. And the non-adaptive setting is saying that I purchase this, so I will try to purchase the Coke for 5 times. Okay, and then I will just realize all of the lotteries and see whether I get a Coke or not. There may be some tiny probability that I do not get a Coke, so this is the non-adaptive setting.
So
Okay.
you're talking about the adaptive or non-adaptive setting now?
So the main result works for both adaptive setting and non-adaptive setting, and the proof goes to the adaptive setting. Okay, so our first theorem says that item pricing gives O log n approximation to the optimal by many revenue for arbitrary correlated distribution over arbitrary valuation function. So we want to emphasize that this result does not need to have any assumption over valuation function, for example, subadditivity or the reliance on the independence of item values. So this result gives a huge improvement to the previous result that proves the same theorem for only the union among buyers. So the O log n gap still seems a bit large, but this is actually what we can do, and this is best what we can do. So we can prove that there exists some distribution over even additive or unit demand valuation, such that for any succinct mechanisms, the simple mechanism M cannot get better than O log n approximation to the optimal by many revenue. And here succinct means any mechanism that can be described by sub-exponential number of bits. So in construct, to get O log n approximation, we only need item pricing that the description complexity is almost linear in N. So the proof of this lower bound results actually highly rely on the description complexity of the value distribution can be very large, exponential, and it is proved using a counting argument that will not be included in the talk.
So theorem 2 has correlated distributions?
Yes, correlated distribution. So for independent distribution, for independent distribution, you can just get constant approximation by a simple mechanism. So this result means that the by many setting actually places huge restrictions to the revenue of the optimal mechanism. So previously, the revenue gap between optimal mechanism and item pricing can be infinite for arbitrary mechanism, but if we force this by many assumption, the revenue gap is going to be O log n. And such gap will hold for the optimal by many mechanism against any simple mechanism we have already studied. For example, some partition pricing, the maximum of item pricing and ground bound pricing, and so on. Okay, so let's go to the proof of the upper bound result. That is, for arbitrary correlated distribution over arbitrary valuation function, item pricing gives O log n approximation to the optimal civil proof revenue. So in this talk, for simplicity, we will focus on proving the result for the optimal deterministic by many mechanism. That is the monotone subadditive pricing. So to prove this theorem, we would like to propose the following lemma that is interesting on its own. So intuitively, what the lemma says is that for any two pricing mechanisms, if one pricing functions point-wise approximate the other pricing function, then the revenue also will have a good approximation. To be more precise, if we have two pricing functions P and Q such that for every set S, Q pointwise C approximates the price of P, then for any value distribution, there exists scaling factor alpha such that we can scale down the pricing function Q by a factor of alpha and get a O log C approximation to the revenue obtained by P. And such lemma can extend to the pricing function over randomized allocation, and this is how we proved the positive result for the adaptive by many setting. So if we have this lemma, then theorem 1 will follow immediately. So if we consider the optimal deterministic by many pricing P, it is a monotone subactive function, and we will define the item pricing Q such that Qi is just the price of the singleton set of P. Then on one hand, since P is subadditive, then P of S is upper bounded by the sum of Qi, which is Q of S. On the other hand, since it is monotone, then P of S is greater than the maximum item price in the set. That is greater than 1 over n times Q of S. So this means that Q just pointwise n approximates P. Then this finished the proof of theorem 1 given the lemma 3. We immediately give the O log n approximation. Okay, so now let's see how to prove this lemma. So we will prove a stronger restatement of the lemma, which says that for any valuation function V, there exists a distribution over scaling factor alpha. I'm sorry, the order is wrong. So there exists a distribution over scaling factor alpha such that for any valuation function V, the revenue of Q scaled down by a factor of alpha, expectation is a O log C approximation to the revenue of P for this valuation function. So if we can prove this restatement, then lemma 3 follows immediately by taking the expectation over all possible V. So it seems like this is just a simple scaling argument. And suppose that the buyer V purchased some optimal sets S star under pricing P, and we can find the scale alpha being a power of 2 between 1 over 2C and 1 such that alpha Q just 2 approximates P of S star. So if we ignore the incentive and assume that buyer still purchased set S star under price alpha times Q, then this is a 2 approximation to the revenue if we correctly guess the scale. And since there are only O log C scales, then this is going to be a O log C approximation. But this ignores the incentive, and the problem is that even if we correctly guess the scale, then the buyer may still want to purchase some other lottery with larger utility and much smaller price. So how do we solve this problem? Intuitively, we observe that the utility can be converted to revenue if the price increases. So what do we mean? So let's see what happens when the scaling factor alpha increases from 1 to C to 1 and observe the utility curve and revenue curve of the buyer. So if there is only one possible set of items that is sold in the menu, then the utility function with respect to alpha is a linear function. It decreases linearly, and at the same time, the revenue function is also a linear function with respect to alpha, and it increases linearly. And at the same time, the decrease in utility is captured exactly by the increase of revenue. So in a menu with multiple options, when alpha increases, the buyer will deviate to purchase some other set of items. And the utility function will be a decreasing piecewise linear function, and each segment corresponds to the same set purchased by the buyer when alpha is in the range. At the same time, we can also observe that the revenue function is also a piecewise linear function, and the increase in revenue is captured exactly by the decrease in utility, but the revenue function may not be continuous. So a good property of the utility function and revenue function is that the gradient of the utility function and the revenue function with respect to alpha is proportional to the revenue function R alpha itself. So if we pick some alpha with a probability with some proper distribution, that is the one with density proportional to 1 over alpha, then we can observe that the expected revenue of alpha, when alpha is following this distribution, is proportional to the integral of the gradient of the utility function. And to be more precise, the expected revenue of alpha when alpha is selected from such distribution is a log C approximation to the utility decrease between the two endpoints, alpha equals to 1 or 2C and alpha equals to 1. So to prove that the expected revenue is a log C approximation to the original revenue, we only need to bound the utility difference. And actually, we can prove that the utility difference between two endpoints is a true approximation to the original revenue. So then we get the log C approximation. So this finishes the proof of the lemma, saying that for two pricing functions P and Q, if Q pointwise C approximates P, then for any so there exists some distribution over scaling factor alpha such that for any valuation function V, the revenue of alpha times Q in expectation is O log C approximation to the revenue of P. Okay, so this is one property of the bi-many maxims. That is, item pricing can give some finite approximation to the optimal revenue compared to the infinite gap we had before for the arbitrary class of mechanism. And there are some other nice properties of bi-many maxims that can be discovered later, and I will mention some here. So for example, to get 1 minus epsilon approximation, what is the menu size needed? The menu size is just the number of menus in the mechanism. So for the non-bi-many mechanism, it is known that when we have correlated item values, the menu size complexity needed is infinite, even if the buyer has additive or unit demand valuation function. And to get finite menu size complexity, here finite means a function of n and epsilon, we need some assumptions for the buyer's valuation function and item values. For example, in later today's talk, there is a result saying that if the buyer has a subadditive valuation function over independent item values, then menu size complexity for getting 1 minus epsilon approximation in revenue is finite. So the good thing for bi-many mechanism is that even if the buyer has arbitrary correlated distribution over arbitrary valuation function, the menu size complexity for getting 1 minus epsilon approximation in revenue is still finite. So this is a good property, but to get exact optimal, the menu size needed is still infinite. So another property that was mentioned in yesterday's Error's talk is about like the revenue continuity of the optimal mechanism. To be more precise, so suppose that we have a value distribution D. If we perturb all of the values in D by a factor of 1 plus minus epsilon multiplicatively, how is the optimal revenue changed compared to the original distribution? So there is a surprising result mentioned in previous talk saying that for non-Byman mechanisms, there exists distribution D and D prime such that D prime is a multiplicatively 1 plus minus epsilon perturbation such that before perturbation, the optimal revenue is infinite, and after perturbation, the revenue immediately becomes finite. So a good property for the Byman mechanism is that this will not happen. It's like the Byman mechanism has a kind of revenue continuity, and it's a good property of the optimal mechanism. And this holds again for arbitrary correlated distribution over arbitrary valuation function. Okay, so I would like to summarize my talk. So we propose an alternate benchmark in the study of optimal mechanism design. And we prove that the Byman mechanism gives significant restriction to the seller and lowers revenue by unbounded large factor. And it also has some good properties. And there are many more interesting properties that can be studied. For example, some properties for the non-Byman maximum, for example, revenue monotonicity, or some better approximation results via simple mechanism for a special case, for example, for a single additive buyer with independent item values, can you get some better result? And a very interesting question here is, when are the Byman maximum optimal? So since it is kind of mathematically simpler to study Byman maximum, if we can recognize a class of mechanisms that a class of distributions such that Byman maximums are optimal on that, then we can just restrict our attention to the study of Byman maximum for those distributions. So another interesting open question is that how do we generalize this to the multi-buyer auction? So this setting is basically like the so for the multi-buyer, multi-item setting with anonymous sequential mechanism, and the Byman assumption is just kind of false name proveness that the buyer cannot create some false identities to participate in this mechanism to get larger revenue, to get larger utility. So there are some results for the false name proveness for example, for the VCG mechanisms. And, but the results are kind of hard to analyze. And we want to ask whether there is a simpler way to extend this definition for the stable proofness. Okay, thank you. I will take the questions.
Other questions?
Hey.
So you talked about if you want to approximate to within epsilon, it only requires a finite menu size.
Right.
Do you have quantitative things?
It's like, so I haven't I will repeat this question. I mentioned that to get 1 minus epsilon approximation in revenue, we only need finite menu size. So what is the quantity with respect to n and epsilon? So I haven't tried to optimize it yet. So it is currently like a doubly exponential, like 2 to the 2 to the n. So to trivially speaking, since there are 2 to the n sets, and let's say there is a additive function over the 2 to the n sets, then the menu size complexity, if you do not do those kind of optimization did by Yanai in this previous stock papers, then it is just trivially doubly exponential. So an interesting question to ask is that whether it can be reduced to singly exponential, because you cannot do a better than exponential due to the lower bound result I mentioned.
So you know you cannot do polynomial?
So that is because to get better than O log n, any small O log n approximation in revenue, you need to have exponential description complexity. So you need to have exponential manual size complexity, right? So actually there may be way to optimize it to be singular exponential because, for example, this kind of revenue continuity bound that works for arbitrarily correlated distribution, but it only depends polynomial in. So it's very possible.